So our speaker today is Nathan Rosenblum. He is a doctoral candidate at UW-Madison. He should be defending this summer. His interests are systems, security, program analysis, and machine learning, particularly the intersection of those. And so today he's going to talk about discovering the provenance of program binaries.
Thank you, Scott. Well summarized. As Scott said, I'm a candidate at University of Wisconsin in Madison. I work with Bart Miller and sometimes with Jerry Drew as well. I work on the Paradigm project, which is a binary tools project. Mostly we do instrumentation and program analysis, binary modification, and so forth. And so I've spent a lot of time over the last 5 years looking at machine code and the weird variations that come up in machine code and so forth. And this has caused me to think very hard some of the time about how these variations arise and what it means and really where code comes from in a number of different aspects. And so, so this has led me to pursue a course of research about where code comes from. Now, people who talk about machine code and the characteristics of machine code at cocktail parties don't get talked to very often, but so you've probably never thought about this before or heard anybody talk about it, but there are a number of other areas where people do talk about provenance that are maybe more interesting. Usually when people talk about provenance, they're talking about like the story of origination of something was discovered, how it's been stored, how it's been transferred, and so on. And so these things are very natural to talk about in the context of fine wines or archaeological artifacts. They're not something that's often applied to or looked at in terms of program binaries or machine code. So I'm sure we can have a lively discussion about an interesting talk about these other subjects. And if I had studied those instead of program analysis, then I would be in a warmer place where it was not winter in April. But since I've done the work that I have in the field that I have, this talk we're going to talk about the provenance of program binaries, not this specific one, but maybe some other ones. So the issue that we start with here, basically, is that in terms of, or from the perspective of somebody who's looking at machine code, the provenance of that code, of like a program binary that you find on your system that shouldn't be there, for example, is really a black box. But there are a number of different questions we can ask about this, and we know something about the way that programs can be generated. So, for example, we know that programs probably were compiled from some source language. There's a lot of different characteristics about this compilation process that you could ask questions about. What was the compiler family? Was it GNU, or was this a Microsoft compiled binary? Which versions, and what options were used, and so forth. What was the source language that people wrote to program in? There's also other aspects of this provenance chain or hierarchy that we think about, which is things like maybe there's code that ends up inside of your program from static linking that says something about the system that you were on. Maybe there's different versions of the Boost library, for example, could show up as differences in the code. And these are all kind of aspects of the way programs are generated. Things can happen after the compilation process. One of the things that we worry about a lot in malware analysis is tools that have been applied to obfuscate or to rewrite binaries after they've been produced. There's also things like the IBM compiler does, or the IBM linker, I suppose, does a lot of whole program optimization. And so these are kind of like the toolchain components of the way that a program was produced from some idea down to the actual executable machine code. One of the things that we think is really interesting to look at, and I'm going to talk about in this talk, is also authorship as an element of provenance. I mean, if you think about it, at the highest level, somebody has an idea for a program, and they make a bunch of different choices about how they're going to implement it, and then run it through this toolchain process. And so the style of a programmer is somehow intrinsically linked to the way that executable code came to be. So in this talk, we're going to cover that, as well as some of the research we've done inferring characteristics of the toolchain that was used to produce program binaries. But before I get into that, I just want to talk really quickly about some sort of immediate applications where provenance questions come up. So say, for example, that you're a software vendor, and you have a buggy program. And I realize this is maybe not the best, so how about this? Say you have a buggy program. And so you have this deployed in some wide distributed scenario, maybe it's an open source project, and you're getting back bug reports. And you need to figure out, of course, how to address these bug reports and what you've done wrong. You feel very guilty. People's computers crash. But what if it's not your fault? What if, for example, there was a buggy compiler used to produce this code, or some sort of subtle incompatibility with other software on the system? And I know, I for one, sort of detect a market uptick in mood when I contemplate this. Maybe it's not my fault that my program crashes. And this is something that's hard to tell because, as if you're an open source vendor, for example, you don't have a lot of control over the production process that your code went through when it was sent out. And maybe you have your build system that distributes your code set up such that it records what the compiler version was that made it, so you can detect whether somebody compiled it with a version of GCC that has a bug in its O3 optimization level. But your program doesn't run in isolation. I mean, it's linked against a lot of other software in these systems that you also don't have control over, and oftentimes, or all the time, don't have annotations associated with them saying exactly what process was used to produce these things. So this is a place where you might want to be able to infer the kind of characteristics of the toolchain that produced the program. The other really pertinent area where this comes up is in software forensics, dealing with malicious codes and software intrusions and this kind of thing. So there's a lot of different work that gets done, of course, in forensics. You have to reverse engineer programs, you do decompilation to try to understand them more. It can be really relevant what kind of tools were used to produce a program, what kind of obfuscations, because maybe you have security analyses that are tailored to specific production chains and that sort of thing. The other question, of course, that comes up in law enforcement and in forensics is who did this intrusion, who produced this tool, that sort of thing. And so, this authorship problem of detecting, if you can, whether a program is written by a particular person or a particular nation state or something like that is a very interesting and relevant question, and it comes back to this issue of provenance. So in this talk, I'm going to talk about how we've been doing work for the last couple of years to recover provenance from executable machine code. The general approach we've used is to build up statistical models of various aspects of the provenance chain, and then to use these things to infer characteristics about binaries for which we don't know, using statistical machine learning techniques. So I'm going to introduce the ways that we represent programs and build up these models, and then go on and give a couple of examples about how we've inferred a lot of details about the compiler toolchain. We've got a process for doing this, and also some work we've done on stylistic attribution, authorship attribution programs from machine code. And then I'll just briefly cover some future directions of this research that are really interesting. I should say now, before we get into it, that if you have any questions at any time, this will be a much more interesting talk if you have me talking about them. So. Okay, so first, modeling. And basically, this is all about how we form representations of programs that pull out characteristics that we can use to figure out how they were produced. Before I get into that, I just need to take a quick digression, and we'll talk about the problem that led us to this whole provenance, especially toolchain provenance issue in the first place, which was, as I alluded to earlier, I work on a tools project that does a lot of binary analysis and instrumentation. And one of the things you have to do if you want to do binary instrumentation, of course, is find out where the code is in the program to begin with. And this sounds really trivial for people who have not worked a lot on binary analysis, but I'll tell you that it's not. Oftentimes you don't have debugging symbols, like if you're working with commercial products, which source code is not available. And so if you want to do instrumentation of these programs, it can be difficult to find the code. Much of it you can find by going through the entry point of the program, but much of it you cannot due to indirect control flow and other issues. And this leaves out, of course, the entire problem of obfuscated codes. And this can be incredibly difficult to find the actual program instructions inside the binary. So the general idea is that we know that there's code somewhere in some object, but we don't know where it is. And the only thing that we have is a stream of bytes. So this whole problem is compounded by the fact that most of the work that gets done in this area, of course, is on the x86 processor and its instruction set. And so that's a very dense instruction set. So for example, if you start parsing a string of bytes, you'll probably come up with a set of valid instructions. If you start parsing from someplace else in an instruction stream, you'll come up with an entirely different stream of instructions that, at least for some time, will be totally different. And some of these are valid instructions, and some of them are not. If you parse data, for example, you can get something that looks like a valid instruction stream, maybe a little bit weird, but it would execute on a machine. So the general challenge that we face is finding code in binaries where we don't know where to start, and if we just start parsing in some random place, then we won't necessarily find what we're looking for. The observation we started with was that there are some regularities in the way that compilers lay out code, like at function entry points, and so we set up an approach where we modeled compiler-specific function entry point preambles, basically looking for regularities in instructions that compilers would emit at the start of functions, and use those to scan for code in binaries. We took a probabilistic modeling approach where we just computed basically the likelihood that any given address in the binary was the entry point to a function based on some properties that I'll get to in just a second, and learned a bunch of weights associated with this model, and we're able to predict this. And it worked pretty well. F1 is a metric that's used for evaluating this kind of information retrieval task. It basically is the mean of precision and recall, how it generalizes accuracy, more or less. And we could do a pretty good job of this depending on the compiler, which is how we figured out that we really needed to be able to figure out from code what compiler produced it, because our models were tied to individual compilers. Let me just briefly say something about the representation that we used for this. We were just looking at sort of instruction level characteristics of the code. As I was saying, you can disassemble x86 code from a point and come up with instructions. And so we came up with this idea of using what we call idiom features to represent characteristics of the code that were associated with function entry points and then with specific choices made by the compiler. It sounds like idioms are supposed to have some sort of semantic content, but I'll just say that that's it's not true. In fact, they don't mean anything in particular. These are just any pattern of instructions up to 3 instructions long that we find in binaries. So there are hundreds of thousands of possible idioms that could exist. There's just a few characteristics I'd like to mention about these things. The first is that they have wildcards, and the second, we have some ways of eliding specific details of the instruction set. There's tons of move operations in x86. We sort of abstract those all down to a single move. Also, we elide immediate values and so forth. There's also an n-gram-based representation just on bytes that we didn't use in some of this early work, but we found very productive later on, even though it's in some ways stupider than the idiom concept. So this was the work that took us into Provenance and sort of informed us that we needed to be able to figure out things about the way that figure out what the compiler was that produced the binary. But we quickly learned through bitter experience that the model of a program that we're using right now, which is basically looking at its bytes and looking at some sort of abstraction over the instructions, is not sufficient. And so we thought about what other ways we can represent the effects that compilers have on programs without sort of a higher level of abstraction. And so we took a look at the properties of the control flow graph. So this is an essential part of our model of programs. The control flow graph is influenced by the compiler in a bunch of different ways, right? It chooses how it can lay out basic blocks and what the contents, the instructions in them are. We also incorporate features having to do with the interprocedural control flow graph, the call graph, the way that functions are laid out in the binary and how they associate with each other. Part of this is dependent on the program structure and what it does, and author preference and how they structure their codes. So you can see how this will come in later for authorship. But also the compiler's choice about how to lay things out There's a lot of variability in there. We also look at external interaction, and this has particular relevance when we look at the way that people's style shows up in code in terms of what external functions they use.
Good question. Sure. You haven't mentioned source language. Was that one of the things that you were also trying to figure out? Like, did this come from C or C++?
Yeah, that's something that we have done, and we'll look at. I have specific examples of that later.
So I think the control flow graph would give you a lot of information about that.
It's absolutely true.
Like for C++, that's a little.
I mean, I think you anticipated a slide that I have later on, but yes.
What about runtimes that are just-in-time compiled?
Well, it's something that we haven't looked at all. So we're looking only at basically compiled C++, C, Fortran kind of codes. I think that the techniques we're describing here could apply just as well. I'm not sure what kind of usage scenario you would have where you would want to do that. I mean, if you're looking at a program that's just in time compiled.
Well, don't the same goals apply to, for example, Java?
Oh yeah, absolutely. Right. So yes, of course. And so I think that you could apply this directly to Java bytecode, for example, as well. If you're trying to do authorship attribution and so forth, and for toolchain analysis to figure out what compiled it. It's just not something that we have directly done. And I think you would probably use slightly different features, of course, but probably not particularly different. Okay, so just to I think wrap up this binary code model, we want to be able to pull out characteristics of these sort of higher level graphical features of programs, but that can be really difficult. I mean, we don't want to do extensive graph matching, this being a pretty hard problem, and so we use some ideas that have been brought up in the both the bioinformatics community and also in the security community in terms of doing matching of or description of programs or other kind of graphical structures using really small subgraphs. So a graphlet we call a graphlet, is a little 3-node connected subgraph of a program where each one of these nodes are some sort of code element. I mean, they could be a basic block at one level representation, or they could be some sort of summary of multiple basic blocks at some other level representation. It doesn't really matter. But the essential elements of graphlets represent nodes somehow that relate to code, and also some typed edges, and the nodes can have colors. And so graphlets are a general sort of template for a variety of different characteristics we can extract from the binary. So one of these that we've used is instruction summary graphlets, where basically each of the nodes here is a basic block, and the color associated with the node is a summary of the kind of instructions that are in it. This is inspired by some work that was done on polymorphic malware detection a few years ago. And so we divided up all of the x86 instructions into 14 different categories, like arithmetic instructions or privileged instructions or branches, that sort of thing. And then just color basic blocks based on the kind of instructions that show up in them. In practice, this is really sparse. You don't have a lot of halt instructions in the same basic block as floating point, and the same basic block as branches, something like that. So there's a relatively few number of colors that show up in this thing. So with these, and then with the instruction level features and some other high level things like the kind of external libraries that are called, we form a small number of templates of ways of describing code. But when you instantiate these things for a given binary, you get an enormous number of features that describe that program, all of the different patterns of instructions that show up in it, all of these little three-node subgraphs of the control flow graph, and so on. And these form the basis for the modeling approach that we're going to use to learn about provenance characteristics. So the general overview of the way that we do modeling basically is to have some amount of code that we're trying to capture. This can be an individual function or an entire binary or some arbitrary segment of a binary in terms of its bytes. And then for each one of these things, there's some associated feature vector. And the feature vector just encodes things like this function contains a sequence that decompiles to push EBP something, or it has some segment of the control flow graph that looks like this graphlet. And so the models we use either can treat these code chunks separately, and we do that sometimes, like look at entire programs and try to classify whether they were written by a particular person. Or we can look at them in concert with other code chunks, like we might do some sort of sequence analysis of a program to find regions of it that are corresponding to a different compiler than other regions of the program. This is just a very general overview of the approaches I'm going to go through in following sections. So the other important part of our modeling approach is doing feature selection. Each of the different types of features we use, as graphlet features, engrams, idioms, and so on, they can instantiate, as I said, into hundreds of thousands or even millions of features over an entire training corpus. And so our general approach, of course, is to cut this down. Otherwise, we run into problems of overfitting the data so that it doesn't generalize well. And so the general approach for this is to extract a bunch of features from training programs and feed them into some sort of large-scale computing infrastructure, which for certain types of feature selection we can do or certain approaches to feature selection we can do to efficiently figure out which features are effective in some way on a tuning set for doing the kind of problems we want to do. So we do this all the time. Yeah.
Have you heard of, and this is, I'm not a machine learning expert, but I heard recently that, and I think this technique's been around for a while, but there's something called support vector machines, which is a way of automatically figuring out what features. It's an algorithm for automatically figuring out what the feature set should be.
Yeah, so
machine learning. Have you given any thought to using that?
Yeah, absolutely. We use support vector machines for a lot of our classification. And so there's two kinds of things going on here with that. The first is that SVMs, and in fact, any other machine learning technique, basically it's going to look at all the features that you give it in this feature space and find the ones that are most important for discriminating, like separating the feature space or forming models and that sort of thing. So any machine learning problem pretty much can be broken down to an optimization problem, and it's going to find parameters that do this. The issue is that if you have an enormous feature space and you have some limited amount of training data, you can effectively run into this problem where the learning problem will fit exactly to your training data, but it won't generalize very well. It'll basically memorize the examples that you give it. And so you want to do some sort of feature selection first to find the optimum number of different features that you can use, or the best features that you can use to get the best generalization performance out of the issue. If you keep adding more, maybe your generalization starts to go down. So in this case, and there's lots of different ways to do feature selection. And some of them are more efficient than others, and some of them are more amenable to parallelization than others. In this case, we use this really heuristic approach to rank features based on sort of the co-occurrance of the training data, and then the selection we do in the large computing infrastructure is to find the number of those that the most you can use without running into problems of generalization. And then the machine learning approach itself, like SVMs or some other model, they figure out which of the features we've selected are the best for fitting.
Nice. So you do an initial culling approach.
That's right.
And then you run that into an SVM
algorithm. Precisely. Okay, so I think that covers the general approach pretty well. So we can get a little more specific if we look at some work we did on recovering properties of the compiler toolchain. So at a high level, you can think of programs as there's a set of choices that you use when you select a way to produce a program. There's a source language, and then that's going to determine which compilers, of course, you can use, and each of those has a version associated with it. And there's lots of options you can use when producing the code. And what we would like to do is to recover paths to go through this. There are some impossible paths I've got listed up here. I don't believe that Microsoft can compile Fortran code, but the GNU compiler can, and so just ignore those. But so the general idea basically is that a program is some path through this space of selections, and a different program might be a different path. And the goal of toolchain provenance recovery is to figure out what these properties were at each level. So as I was saying earlier, we came to this problem because we wanted to use our compiler-specific function entry point models to figure out where code was in binaries, and we couldn't do that. So the first way we approached toolchain recovery was looking at programs as just a sequence of bytes. And we're trying to figure out whether the Intel compiler or the Microsoft compiler or the GNU compiler was used to produce them. So the idea is that a program can be made up of segments of code at the sort of compilation unit level produced by different compilers. And we don't know what those might be. It's just a blank sequence of bytes. And so the general model we use for looking at this is that as you scroll along through this code, at some point there's an inflection point where these bytes were produced by a different compiler. Like the case where this commonly comes up just in normal practice is if you compile a program using the Intel compiler on Linux, there's some statically linked code from the glibc that makes its way into your binary, usually at the beginning and end, in terms of constructing various data structures for the operating system, and those are usually produced by like the GNU compiler. So anyway, the notion is that we're going to find parts of the sequence that correspond to one compiler or one to another. We did this by every byte sort of assigning to it a node in a probabilistic model and associating these things with sequence labels, like Intel compiler, GCC, data, that sort of thing. The features we use were these idiom features, which of course correspond to instructions, and so they span more than just the single byte in the binary. We are just labeling this individual byte one at a time. So since this is a joint model, we used what's called a conditional random field. And just really quickly talk about this. It's not terribly important, the details. So if you're familiar, of course, you can just ignore what I'm saying. But a CRF is it's a probabilistic graphical model, which means that there's probabilistic dependencies between things in it. And basically, it's going to assign a probability to a set of labels based on some evidence. And this is going to be based on both feature functions and a set of weights which are learned. The feature functions are just what I was introducing earlier. If there's an idiom, for example, the feature function might be 1 if a particular sequence of byte of instructions exists decompiled in a byte, and 0 otherwise. And the CRF's job is to learn the weights associated with this so that you can make a probabilistic estimate of what labels should be applied to a sequence. So for this, we use what's called a linear chain CRF, which it's like a Markov chain. Basically, there's each node, each byte is sort of conditionally dependent on its neighbors and nothing else. The gray nodes in this picture are the data, but that's not important. This is really nice because exact inference in this kind of model is a tractable thing to do, whereas in general, structured probabilistic models it is not tractable. So what we do is learn through training data models that model sequences of code-generated conditional compilers, and we evaluated this by both by looking at programs that were naturally compiled by different compilers, and also programs that contained code from multiple different compilers by linking together code where each compilation unit, each source file, is produced by either ICC or GCC randomly, and then linking these things together. So we can do this with actually, it turns out to be quite high accuracy. We get about 94% accuracy labeling these sequences. And this gives us about 18% improvement over the task of finding code in binaries. So we tried creating a model basically to find code that was independent of the kind of compiler that produced it, and we got almost a 20% increase in its accuracy by feeding in this prior knowledge of which compiler produced it. So once we knew how to do this, we wondered, if there was possible to find out more details about the my keyboard quit working, about the compiler that produced this. So here we've been looking at the compiler family, and we wanted to add in things like the source language that you asked about, or the version of compiler produced, or its optimization level as an example of things you might wonder about the options being used. We use the same kind of model, but in this case, we're not looking for code. We know where it is already, and we're trying to do some sort of higher level analysis of it. So we cut the program up into functions instead of,
How detailed are you on optimization level?
This study was just low versus high. Like we lumped together O0 and O1 and O2 and O3 in GCC. We haven't looked at whether you can look at for particular optimizations. I think that you probably, some of them should come out pretty clearly, and some of them probably less so. So like loop on roll, I think would come out pretty clearly.
Right.
And probably, I mean, if you think about the difference between O1 and O2 in GCC, I think it's probably a lot where the distinctions come up in terms of sort of more aggressive optimizations that have more to do with. I mean, at some point, it has to be about the instructions that are emitted. So anything that causes a huge variance in the distribution of instructions that are emitted is something that shows up here. That's what we'll do in a second. So this approach was actually quite similar to what we did when we were looking at the byte sequences, except we're looking at functions. So functions are the unit that we're labeling now as opposed to individual bytes. We tried a much more complicated graphical model, which is this grid structure, where we're sort of independently labeling the language and the compiler family, optimization level of the version, using both idiom and the graphlet features that I introduced, because one of the things we've observed just by looking at binary code that's produced by compilers is that different versions of the compiler tend to do things like reorder the way that branches are laid out, for example, in loops. This comes up quite a bit. So we evaluated this on a large set of programs, looking at 3 different ways of doing this thing. The first is just using SPMs to individually classify functions for each of these different components without incorporating any information about the adjacent functions laid out in the binary. And so we get pretty high results with that, with everything except for the version. The basic power of incorporating these CRFs basically is that it allows you to incorporate sort of the structure of the high-level structure of the program. And it's conceptually, I think it's pretty simple. It's more likely that 2 functions that are adjacent in the binary were produced by the same compiler. The second 2 columns are both conditional random fields. The first, this is in blue with the better scores, is one where we're treating each of these components separately and not doing this whole joint grid structure model that I showed in the previous slide. And this turns out to be the best way to do it. So you can wonder why I'm presenting anything about this more complicated model at all, especially because it's slow to do and it's approximate. And it also can give you possibly inconsistent labels, like it can tell you that a function was produced by, it's written in C and produced by GCC, version 2005, low optimization, which is 2005 is a Microsoft compiler version, and so forth. So this can be kind of weird. And the reason that we looked at this at all is because it allows you to get sort of partial label results. And it allows you to, so it can give you these labels like C, GCC, 2005, and low, and it can give you marginal probabilities over these things. So you have high confidence that it was written in C, you have high confidence that it was in GCC, high confidence that it's a low optimized program, and maybe really low confidence, just barely 2005 wins out. And so it gives you a joint way to deal with this. But in practice, we find that the trade-off in terms of performance is such that we're willing to sacrifice this kind of flexibility in the model for much faster runtime.
How do you, can you explain like the huge jump you get in improvement on the version?
Yes.
Between the 2?
Yes, I can. Version is very difficult to tell apart. Especially if you get down to like minor versions of the GNU compiler, there's no difference in the code being laid out because they're usually just minor bug fixes. But the majority of the difference here in this number has to do with the Microsoft compiler. So at the high level, the reason that we do so much better with linear chain CRF is that basically you can think of these Markov like probabilistic models as sort of having inertia. So if it's really clear for one function, and then it's less clear for the one adjacent to it, well, it gets to be conditionally dependent on the one that's nearby to, so that sort of drags up the probability of prediction over here. But what's going on in these numbers is that for the Microsoft compiler, there's very little variance in the code emitted across different versions. If you look at 2003 to 2005, sometimes in some programs you'll get something like 70% bitwise identical code being emitted. So there's not a lot of churn in the code that's emitted from different versions of the Microsoft compiler. The code generation engine basically doesn't change very much, which we thought was an interesting result in and of itself. If you look at the GNU compiler, if you look from 3.4 to 3.6 or something like that, the code is radically different. There's a huge amount of churn going on in terms of the code generation engines of those compilers.
So, sorry, I still don't understand
Okay.
what the. Maybe you answered it and I missed the answer.
Can you
or the question was, why did using these CRFs dramatically increase the version?
Yeah. So
I guess I didn't absorb your answer.
Sure, no, it's fine. I don't have a slide to show this, but basically, sometimes we're looking at so this number here, the individually column. This is looking at sort of each function individually and saying, can I correctly classify the version?
Okay.
And then the CRF, each adjacent function inside of a binary is related to, like, the prediction that's going to be made about that is going to be related to the ones that are adjacent to it.
Okay.
And so for some of these, it may not be very clear at all, and so it's kind of random chance whether it chooses 2003, 2005. And then for some of these, it's going to be much clearer. And so the prediction for the one where it's not clear by itself is influenced by the properties of the one that's adjacent to it. And so that has this sort of inertia effect where functions that are close to each other get assigned the same label. And so
right. I understand the improvement, but why the difference between the top three? The improvement in the top three is very small. The improvement in the version is huge. So
right.
What is it about the version that makes it so sensitive to the looking at the adjacent?
The answer is that it's just much harder to predict the version. There's much less variation in terms of like going from, especially in the Microsoft compiler, going from one version to another. So basically, you can imagine that for most functions in a binary, sort of it's sort of like random chance, even chance of which one would be assigned. And then but then for some of them, it's very strong, and so those tend to, when you look at them all together in the sequence, they tend to force everything to flip to the correct assignment. And so you get a big jump in there. The rest of these things, it's relatively easy to tell the difference, and so there's not much room for improvement. So it's really easy to tell the difference between different compilers or different optimization levels of the same compiler. The code is radically different.
So it seems like this is saying something very specific about the difference between versions of compilers, and that it has to do with placement of functions.
Well, I thought you said that the version was so low on SVM because it was sort of pulled down by the Microsoft compiler.
Well,
that's one of the reasons it was so poor.
It's also poor poorer in the GCC and ICC results as well. It's really bad in the Microsoft. What this is saying, I think, another way to look at this is that there's relatively little variability between versions in terms of code generation for compilers. And I guess we kind of hope that to be the case. We kind of hope that we're getting close to figuring out how to do this at this point. But in some cases, when you look at the linear CRF results, in some cases the variation can be pretty strong. So imagine there's some code constructs that show up in some functions that lead to radically different code being emitted, and that's what's causing this kind of model to sort of boost up. I hope that answers your question. We can.
Yeah, we can take it offline later.
Yeah. So I'm going to shift gears now a little bit and talk about some more recent work that we've been doing in authorship attribution. So we looked at the toolchain and inferring these components. And I'll just say from the beginning that we didn't have a lot of hope that this was going to work out. We were quite surprised at the results we get. But basically the idea here is that we want to see if you can tell characteristics about the person who wrote a program by looking at their executable code. So the general idea here is that there's a couple of different people and they write maybe the same program, and we have sort of intuition that everybody writes programs a little bit differently. I mean, you work with other people and after a while you can kind of recognize their code, for better or worse. But so for example here, like these two guys have decided to write this iteration over something using slightly different means. One of them is obviously using C++, the other one maybe is not. And there's been research over the last decade or so occasionally about whether or not you can tell, you can do authorship attribution of programs based on their source code. I mean, this is something that has a long history of use in literature, and I think there's a Dan Brown novel or maybe a movie coming out about this. I'm not sure, Shakespeare, something like that. But anyway, it's something that people have been interested in literature for a while, and more recently interested in terms of program analysis. But it's all been done at the source code level, and you can kind of get a sense of why it would work. Well, our hypothesis is that the kind of differences that people use in the way they program is something that shows up in binary code as well. And we have some things to back us up on that. So we looked at some programs that were doing the same sort of thing. They represent the same functionality. In fact, Google helped us with this quite a bit, as I'll get to in a minute. And then we compiled them down and took a look at their control flow graphs. And just looking at these things, you can see that there ought to be properties that we can extract that say something about how this code is different. I mean, one of these guys is using STL, and as you mentioned earlier, it's full of small functions and lots of ranges and so forth. The other one was written in C, and it's much less complex, but they do the same thing. So before we could capture this, we needed some additional features about the code to try to catch more about the way that people make decisions, the way they structure their programs. And what we decided to do was to try to incorporate more long-range control flow information. Our intuition being that people, the way that people structure the control flow of their programs is more important. So recall that we had these graphs that are just basic blocks, and we had these instruction summary graphlets we used in toolchain analysis that were like 3 connected subgraphs. And so one way to get longer range information is just to condense these things down. We use a process where we basically select any 3 nodes that are connected and then incorporate their neighbors. And then so that the colors of these nodes would become the summaries of the union of the neighbors. And we can do this recursively to get sort of arbitrarily long distance control flow information condensed down to these 3 graphlets. We're really focused on the sort of size 3 graphlets because we can leverage some properties of the structure of them to make the subgraph matching problem a little bit cheaper. So this is one way we've incorporated longer range information. And there's another one is to incorporate the sort of interprocedural control flow, like the way that people structure relationships between functions in their program and relationships with outside functions. We created these call graphlets, we call them, which are created basically by doing a reachability analysis on nodes that make calls in the program, and ends up with you having something that's a DAFA for recognizing call sequences, where the color of each of these nodes has to do with the external call target or local methods, which are anonymous because they don't translate from program to program. So these are just a couple of additional ways we represent code for this authorship authorship analysis. So learning about program authorship and evaluating it can be really difficult because getting a hold of an ideal data set is really hard. Obviously, you need something where there's author labels, and so one possible source of that is open source projects, but it's really difficult to mine. I'll just tell you, it's really difficult to mine open source projects for sort of author-associated code information, and to have it be consistent, especially with the way these things churn, people copy and paste code, and so forth. You also like to have a parallel corpus, and this is mostly for evaluation. You want people to be implementing the same programs so that you can control for compounding variables like the fact that they're using different functionality. And linguistic homogeneity, like people writing in C or C++ or something, same thing. You have control for compounding information. So we found a couple of good corpora for this, and one of these was the Code Jam competition. I talked to I talked to Nina, I think, first, and a very helpful engineer who suggested ways to just scrape all the data from the Code Jam competition, so that's exactly what we did. We also used some programs from a operating systems course at University of Wisconsin. These data sets are a little bit different from each other. The Code Jam, we got a couple of years worth of contest data, and we just extracted all of the programs that were written in C++ or C and would compile with the compiler version installed on my workstation, so without modification. So that was relatively few, but it's a few hundred people per year had, between 8 and 16 submissions to the Code Jam competition and met these criteria in terms of using C and C++, compiling on the machine. So the bottom here is a distribution of the number of programs available per person. The CS537 course, everything was written in C, and there were remarkably fewer examples. I think that there were something like 8 projects in the class. Nobody had more than 7 completed, or that I could build, and quite a few people had less than 7. I guess dropped the course. There's also some differences here, which is that a lot of the 537 code has got provided template code that they started with for these projects, and so this ends up making the learning problem a lot more difficult.
What about some of the beginning programming classes? I mean, I'm sure that thought came up.
Yeah, it certainly
Why did you
did.
reject those?
But most of those are done in Java at WISC, and so since we were working on executable code, certainly something we're working on. So first thing we did was try to do authorship attribution, and basically we mined these program data sets for all of their features, and there's a large number of these things. And we used the feature selection process that I alluded to earlier to reduce this to a set of 1900, and we used support vector machines to further define models and to do classification. So the procedure we used was to take 20 programmers at random from these data sets, and take all of their programs and form data files from them, and repeat this kind of experimentation 20 times. What we found was that with somewhere in the high 70s accuracy on the Code Jam data set, we can tell an individual person based on their machine code. And this sort of generalizes across any selection of random programmers that we got. The 537 data set turns out to be much harder. So we also evaluated how well we can pick out the right author in the top 5 of the most likely authors based on the classification method. This is because operationally you would want to be able to do something like this, I think, from malware identification. You're trying to find the most likely candidates. So when we do that, we get relatively high scores, both the Code Jam examples, and somewhat higher on 537, but it still remains a difficult data set. And so one of the conclusions that might be tempting to draw from this is that students have less distinctive styles of programming, but I don't think you can get there. The first is that the 537 data set has much less data per person. So it admits a kind of training scenario in which there's just really not enough information to learn exactly what style a person has from their code, which is not training data. And the second thing is there's a lot of template code provided, and we worked as best we could to eliminate this stuff, but I don't think we did a perfect job. And then if you observe people being taught in these courses, the instructor is sort of guiding people in the way to do the programs, and they have a lot of feedback. And so I think there's something involved there. Whereas the code jam is this individual contest competition. So authorship identification like this is one interesting application. But another thing you could try to do is cluster programs with style without knowing who particular authors are. So this has relevancy in the malware world. If you are looking at like a large set of malicious software that exists in the current computing environment, and you would like to know whether you can group programs based on stylistic characteristics to maybe see that there's multiple different groups working, or malicious software authors, that sort of thing. This is a really challenging problem because you don't have any training data to do this with. You would like to be able to take a bunch of programs and split them up into clusters and say, okay, we have a couple of different authors. But you just as well might have a scenario where you found the fact that there's programs that have functionality, and you're just clustering based on that. And so, how to cluster these things automatically without training data is a really difficult problem. So, just really quickly go through this approach, which is the notion here with clustering in general is that you're going to find things that are sort of nearby to one another in some space and far apart from other clusters in some other space. So in this totally contrived data example, we have a couple of different groups with possible clusters, but they're no more likely than some other groups with that could be assigned to with clusters. So one way to approach this is through what's called distance learning. The Mahalanobis distance is a generalized distance metric where basically data they go through some sort of transformation. So for example, one way to transform these data points is to squish down the y direction so that the clusters that you would draw from this data are much more obvious. There's not a lot of ambiguity there. Of course, the question for this kind of approach is how do you get this A distance metric matrix, especially if you don't have a lot of training data. And so the approach that we took for this study was to realize that we do have training data in a sense. We have some programs that know who the authors were. And if we could somehow learn a way to transform data so that style is the important dimension of this problem, then we can maybe apply it to something else. So what we do basically is without going into a lot of detail, we learn a distance metric that separates programs in a style space, and then apply that to the data for other programs, and then find that they separate into style as well without having any kind of information about the people who wrote these original programs. We used some relatively recent work on finding distance metrics in this kind of scenario. It's called the large margin nearest neighbors method. Unfortunately, this requires solving a semi-definite program, and it's kind of expensive to do. Although this is sort of a one-time cost, and so it has no real effect on the scalability or performance of our actual clustering algorithm. So we evaluated this on one of the CodeJam data sets. And this is a comparison of doing clustering, I guess k-means clustering, on either data using like Euclidean distances in the feature space or this learned metric. And what we found is that as we increase the number of training set authors, we get better metrics. This is pretty straightforward. And furthermore, that we get sort of stable improvement by using this metric when we have different numbers of authors in the test set. So the takeaway here is that we get something like a 20% improvement by incorporating the stylistic information. And this tells us is that we can, in fact, learn to recognize the stylistic characteristics of binaries in such a way that they generalize to different sets of binaries written by different people. In general, we get the normalized mutual information is it's just a metric for evaluating clustering. 1 is better. We get about 7 to 3 on this problem, which is pretty good, but it's certainly not perfect. And this is it's a very difficult problem in general, I think, to pick out author style in these programs. So I'm just about out of time here, I'll just touch really quickly on a couple of different future directions for this work. The first is, one of the assumptions we've been making this entire time is that sort of, especially with regards to the authors, is that people write like an entire program by themselves. But I think that's obviously not true. And I think that especially there's a lot of research being done in the malware community, or the anti-malware community, about the way that that components are sort of being shared around by different malware projects. Like command and control software for botnets sort of moves around between different botnets. And so one thing it would be interesting to do is to see if you can track this kind of relationship based on the stylistic properties or toolchain properties of the compiled code. Another thing would be that we've sort of assumed that each person has one style of programming, but that may not be true. It could be that people have different styles for programming, and they use different approaches when they're tackling different tasks. And so this raises a lot of different questions about how you can tell style versus functionality in programs apart. I think it has a lot of applications for some recent research into some more advanced machine learning techniques. And it brings up this issue of how to interpret the clusters that form when you cluster based on stylistic information. Another really fascinating, I think, application of this is looking into the sort of the social network of the underground malware economy. I mean, if you assume you have a bunch of programs and some number of authors out there who are writing these things, or nation states or groups or whatnot, it may be possible to sort of segment these programs based on stylistic characteristics, and from this to infer relationships between the groups that are producing Stuxnet, for example, and the groups that are producing some other piece of malicious software. So I think this is an area where there's probably productive work to be done. Anyway, just to sum up, the approach we've been using is to use many different simple features of programs, a huge number of templates, and to take advantage of the structure of the program to do things like that we find relatively surprising, like detect author style in program binaries. So with that, I can take any questions.